Okay, can everybody hear me? Just say something in the chat if you can.
Yeah, it works.
Very good. Now, for some reason, I've lost my chat. Let's see here. Chat. Share screen. Okay, good. I think, well, good news, I don't have COVID. It feels like maybe COVID has burned itself out, but I was sick, so that wasn't so great. All right, I trust that everybody got recitation 4, recitation 2. Recitation 4 will be the last one, but that's a ways off. Recitation 2, sorry, so I'm not completely over it, but yeah, so if there's any questions about recitation 2, please post them. I can answer quick questions, but I hope that everybody was able to build the data file, you know, the representing a galaxy, which I thought was kind of fun. So I'm assuming that everybody's going to be that's succeeding for everybody. But. All right. Okay. So today we're going to talk about transactions, and this is going to be the first lecture on transactions, and the next time we're going to talk about actually what transactions look like now, modern day. But this theory is necessary to understand before we look at the way transactions are actually implemented in modern systems. So yeah. So what is the issue of concurrency in databases? So yeah. So it's there's many applications. The database has to be accessed by many users simultaneously. So really, if you think about almost all modern uses of databases, you need to have concurrent users. So, you know, like for instance, lots of different updates can be made on a financial database from different parties. So so really, there can only be one user. There can only be you can't have it so there's only one user at a time. You have to let multiple users access the database. All right, if this is just read only though, then it's not really a problem. So like, you know, that certainly is the model with like say websites where somebody goes and they make a call to the web server, they get a copy of the HTML on the website or on a page of the website, and then another user does the same thing almost simultaneously, and they interweave their exploration of or intertwine their exploration of the database at the same time. In that case, they're just doing reads, right? They're just doing reads, so it's not a problem. But if you're going to be writing, then you might have some serious problems, okay? So, so actually you might say that when multiple users are accessing a website, they might be writing logs simultaneously, so you need to synchronize the access to the log so you don't get problems. So, you know, so there's already kind of some notion of concurrency just in terms of locking semaphores, this kind of stuff inside of operating systems. But in databases, it has to be much more sophisticated because we're talking about access to things at different levels of granularity, like records or ranges in tables or tables themselves, or even the database. So we need to kind of delve into this and kind of get some kind of study of what a transaction is, and then try to categorize what should be the correct behavior of a system where you have multiple users doing reads and writes. Okay, so I'm sure a lot of you have heard this ACID characterization. So a transaction system is, you know, ACID if it respects each of these properties, where A stands for atomicity. So this means that basically a transaction either fully executes or it doesn't, right? So you don't have any partial execution of a transaction. So I think some people, like, maybe it seems very low probability, but in recitation 2, when you make the portals in the space system, there's a chance there's going to be a collision on portals, because you know there's a functional dependency that stars can only have one portal that they're going from. If it happens that you just randomly have two stars that collide, then what you'll notice is that nothing got added. So that is respecting atomicity. So if the transaction messes up, you don't take the partial results and let those go through. It's just like either the whole thing goes through or not. All right. Oh, and by the way, just so you know, you've been using transactions already, whether you know it or not. So implicitly, every SQL command you've ever issued had a begin and a commit after it. So these are very simple transactions, but but that's kind of implicitly what's going on inside of SQL. All right. Consistency then also is that the foreign key and primary key constraints of the database are respected before the transaction and also after the transaction. So the transaction doesn't leave the database in some kind of inconsistent state. All right, so it maintains the integrity. Now, as it turns out, it may, during the transaction, there may be some suspension of the, or they might defer some of the foreign key and primary key constraints. So it doesn't necessarily actually have to be consistent during the transaction, but certainly at the beginning of the transaction, at the end of the transaction, it needs to maintain consistency in the database. All right, now there's the issue of isolation. So the isolation of all the ACID properties, isolation is the one that can wiggle a little bit. So this is the one that there's different variations of isolation levels, okay? So isolation, though, if we just think about it kind of in the abstract sense, isolation is like the feeling or it's when a transaction does its work and it can do it as if there's nobody else, no other transactions running concurrently. All right, so at least from the point of view of that transaction, it's perfectly isolated. So it doesn't have to worry about what other transactions are doing. Isolation is actually kind of a deep concept. In fact, the modern world in some ways operates under the principle of isolation. That is, we don't want to, when we go to the grocery store and we want to buy milk and cheese and all this other stuff, we don't want to really have to care about other people. Sorry. We want to be isolated from them when we do our work. So if you're doing work on your code or something, or you're doing work on some system somewhere, you'd like to have the feeling that you're completely isolated from other people, so that you can actually get your, so you can have a kind of a stable system that you're working over. So if as you're working, things are changing in the environment because you're not isolated from others, that can make your work harder. All right. So the same is true with transactions. And then finally, there's durability. So durability is really important. So what it means then, it means that when the transaction commits, so when you've gone through a transaction, you've committed the transaction, and the system has said, yes, this is successful, that it won't later on roll that back. So the durability is extremely important. It means that basically you can trust assured that actually after doing the transaction, then it's stuck. I mean, it's not going to be undone. Unfortunately, in the world, I don't know if you guys have the experience, but I have experience with certain usually big businesses, that I change my address with them like 3 or 4 times before it finally sticks. So it's like, yeah, you've changed your address, but then later on they're still sending to the old address. All right. So that's showing that in the real world, sometimes you don't have durability on your transactions, unfortunately. All right, so let's look at some example transactions here. And this is kind of going to be a little bit like, this is going to be kind of, this is going to be the beginning of some kind of notation we're going to develop here. So we have transactions 1 and 2. So T sub 1 and T sub 2. That's how we denote separate transactions. And then we have the operations read and write. And sub I is which transaction is doing it. And then that might also be over a that might be over a specific variable, but we'll see this in a second here. So let's just consider the following operations. Okay, so we're going to define these in kind of pseudocode in some sense. We have a read balance. So this is when a transaction I reads the balance of A. All right. So what this basically is doing then is it's loading the amount of the balance of A into a local variable. All right, and that local variable is R sub I. Then we have the writing out of the balance of A, and what that's doing then is that's taking whatever's in the this local variable W sub I is writing it out to the balance. Okay, and then we have the notion of compounding the balance. So that basically we're going to put like a certain percentage increase in the balance, and then we have the idea of withdrawing the balance. So let's just consider that what transaction 1 wants to do is it wants to compound 10% on the account 15. So the first thing it's going to do, it's going to read the balance of 15. Okay, so it's going to read 15 in. What's the balance of that? Then it's going to, inside that local variable, it's going to compound that balance by 10%. It's going to add 10% to whatever is there, and then it's going to write that back out to the database. Don't worry about tables at this point. Just consider that there's just one. There's only actually one table here. It's just the table of the bank balances. And in fact, don't worry too much about the notation here, because we're going to go to a better notation, which will be kind of an interesting, kind of a pretty deep insight that actually got that was most of the way toward getting one of the major prizes in computer science. So upcoming is a pretty significant, back in its time at least, was a pretty significant discovery. All right. Anyways, so we have these, we have these kind of pseudocodes, we have these local variables, we have the kind of complexity that we're dealing with here. We have compound 10%, so that read the balance of 15, compound it by 10%, and then write it back out. Now we're going to have another one where we're going to withdraw 2,000 crowns from account number 15. So we're going to read the balance of 15, we're going to withdraw 2,000 from it, and then we're going to write it back out. Okay? So here are two possible schedules for the transactions. And these both make sense. The bank has the right to execute these in either order, and you have no right to complain. So if these two things are happening, and it turns out that that what the bank does is it says it's going to run transaction 1 first. So it's going to do the compounding of 10%. And then it's going to do that. So compounds that the bank balance up to 11,000. And then it's going to then run the second transaction where it's going to do the withdrawal. And so the final balance, ending balance, will be 9,000 if you think about it, right? Now, another way of running it, so let's say these are both getting logged on the same day. There's a withdrawal coming in, or you're paying something, and also there's a compound action happening the same day as well. So, well, the other way the bank could run it is the following way. It could run the withdrawal first, so it could take the 2,000 crowns out first, and then do the compounding. And I think maybe the bank would prefer the second schedule, if you think about it from their point of view, and you might prefer the first schedule. But you don't have a right to complain, and they don't have a right to complain if it happens to go one way or the other, okay? Because they both make sense. They're both reasonable, all right? I wonder actually if banks make it so they always do this, if they have the choice. They probably do. That would be a very quick optimization that they probably have put into their system to do some extra transaction ordering. To make more money. They have the they have the power to do that. All right, now, however, if we allow for concurrency, so we allow for both transactions to run simultaneously, we can get basically what's called the lost update problem. Okay, so what's happening here is that one of the transactions is doing its right, and then it's getting clobbered by the one next, by the other transaction. Okay, so in this case here, what we see here is transaction 1 does the compound inside of its local memory here, and then in sneaks number 2 where it withdraws the 2,000, and then finally, so it updates the database value for the account to the balance of account number 15 to 8,000 here. But then along comes, as it's part of this transaction that's running here, this transaction T1, along comes this right here, and it clobbers the 8,000 and puts 11,000 in its place. Okay. So this would be good for the customer, bad for the bank. But the bank would have a right now to say, well, that wasn't really intended. This is, in some ways, this is not a meaningful, this is clearly a bug, right? An update was overwritten, clearly a bug. Now, this might also be here this might actually be this is another possibility here, where the update after the withdrawal clobbers the compounding update. Okay, so both of these cases are bad. They're bad in the sense that they don't make any sense. They don't make any sense. So if you assume these are isolated transactions, neither transaction should be happy, because the results being yielded, well, maybe one of the transactions should be happy. T2 here should be happy because it's like, well, yeah, I started out with 10,000, I got down to 8,000. That makes sense. But T1 might look in here and say, well, I mean, after the fact, everything's done, it's like, well, where's my compounding? I was lost. So they don't like that. All right, so I hope that you understand this is just something that shouldn't be permitted. Okay, so now the great insight of Gray was that it doesn't, that these internal steps, these read balance, write balance, and these local variables, you don't even need to represent those to get to the root of what a transaction is and to start dealing with the theory of transactions and how to handle these problems. The problem we're looking at right now is this lost update, the clobbering of one value by the other. So what we see here then is we see that what Gray was able to do is to abstract all the potential complexities of internal variables and compounding things and all this other stuff, and just say it's all about reads and writes. That's all you need to consider is the data object and whether it's a read or a write. That's all. That's all you need to consider. And that's pretty insightful, actually, because once you do that, then impressively, the theory actually applies back to all the special cases. We're actually doing special things with local variables, and you're doing very idiosyncratic things of your particular domain. So this abstraction level allows you to really abstract away from a lot of the specifics of one particular case. All right, so basically we just have some definitions here. So the basic step of a transaction then is either a read of something or a write of something, period. That's all we have to consider. So the actual values are not important. The internal steps are not represented, so you don't have to, these complex steps aren't represented. Only the fact that it's a read, that T either read or wrote the object is important, right? So the way we're going to write this is basically read sub I. So if transaction 1 reads X, it's going to be R sub 1 of X. And likewise, if they write X, it'll be W sub 1 of X, right? So a transaction itself, so an actual transaction, is just going to be a finite sequence of steps. So it's in order, right? So you can't change the order with inside the transaction itself. Otherwise, it makes no sense. But basically, it's just a set of steps, a sequence of steps, and then a sequence of steps, which is represented as basically just a sequence here. T1. These are the operations there. Okay, so so T1, this is the one potential transaction here would be to read X, to read Y, to write Z. Okay, so Z is completely something different. So it's blindly writing Z. So it's not even reading Z, it's just blindly writing Z. Okay. If you want to turn it into a set, though, you can say steps. So this is just it will help with the notation. It's nothing complicated here. So if you apply steps to a transaction, you'll get out the set of the transaction. All right, so now we'll talk about a schedule. All right, so we have more than one transaction, of course. So what we're going to talk about now is we're going to talk about a schedule of steps. All right, so just say we have M transactions. All right, M simultaneous transactions. And let me just go right here. Let me just show right here. T sub 1 is going to be read 1 X and write 1. Okay, I hope this makes sense. So in that prior example where we had the compounding and we had the withdraw, what we have is basically the following. It's really simple. There's only one data object. It was that account balance 15. And I hope you guys, this makes sense. It's basically what transaction 1 was. Let's say that's the compounding one. It was reading the value of account number 15. We call that X. And then it was writing it. All right. And likewise, it was account number 2, or I'm sorry, transaction number 2 was reading account number 15 and then writing account number 15. Okay. And I'll show you the schedule. I'll show you a schedule in 1 second. So those are two transactions. So we have 1 and 2 there. And then basically what a schedule is then, is a schedule is basically a sequence of, it's a sequence of steps such that the total ordering on the steps has the property that any operation or any read or write that happened inside the one particular transaction, if the operation happened before the other operation, then it has to be before the other operation in the schedule. So let's just show this. I think maybe we'll show. I just want to show this really simple example here of a schedule. So this could be a potential schedule here. Here's a schedule. S equals read sub 1 of X, read sub 2 of X, and then write sub 2 of X, and write sub 1 of X. Okay. I'll just make my sequence. I'll use Python notation. Okay, so what this has done is, it's really simple what it's done. It's just interleave, it's taken these here, and now it still is, now if this operation happens before this operation in the transaction, it's also gonna happen before this operation in the schedule. So is this operation, is it happening before that operation? Yes, it is, okay. So if I had this would not be, this is not a legal schedule. I'm sure that everybody realizes this, right? That is not a legal schedule, because it went in, it permuted it switched around the order of the operations inside of transaction 1. I mean, I hope this is clear. Okay, so this is the schedule. That's a schedule, all right? This is a bad schedule, by the way, and we'll come into why it's bad in a second, but that's a schedule. So let's look at some other schedules here. So if we have 3 transactions here, there's some reading of X, right, reading of Y, writing of X, writing of Y, et cetera, et cetera. Then this right here is certainly a schedule. And this is a special kind of schedule. So, so basically all right, the first thing we have to say is okay, these are all the operations, all the steps, right? There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And there should be 11 here, okay, because we're not missing anything. And if something happens, so this R3 of Z is right here, and W3, okay, X. So it's basically keeping them in order here. That's fine. But what's special about this particular schedule is that it's serial. All right, this is a serial schedule, because this is the schedule that gets represented if we pick some ordering on the actual transactions. Okay, that's what's called a serial schedule. All right, so because this is the ordering here. This is the ordering of the serial schedule. So if I go back here, this is not a serial schedule, because this R1 starting, then R2 does I'm sorry, T1 starts, then T2 does its business, and then T1 resumes. So that's not serial. Had it been that is a serial schedule, all right, with 1 going first and then 2 going, all right. All right, so this schedule down here is not serial. This is a schedule where things are being intertwined. All right, so the notion, if we want to have concurrency, though, we're going to have to let things intertwine. Otherwise, I mean, the easiest way to get serial schedules is just to simply say that, well, you have a set of transactions. You say, okay, you run all the way to completion, then you run all the way to completion, then you run all the way to completion, and that will enforce a serial schedule. That, in a sense, that's just basically locking the whole database, right? But that's not realistic. So, for instance, we might have a situation where we have a bunch of people looking to book planes or book travel. So you don't want to sit there and say, well, wait your turn to even start looking around for tickets. You don't want to say that, because I might be looking for tickets to fly from Umeå to Gran Canaria. Somebody else might be looking for tickets to fly from Stockholm to Thailand. And, well, we really shouldn't contend over anything, so we should be allowed to go simultaneously. All right. So this idea of just basically saying every transaction has to, you wait your turn to even start reading and writing and all that is unrealistic. Also, I might open it up and start looking around and then go get a cup of coffee. So I'm not completing my transaction, whereas other people want to come in and get their work done. All right. So So you don't want to be, you want to be isolated from other people's delays. All right, so serializability then, so again, we're going to have this. We want to have this in the real world. We want to have this intertwining. So we don't want to have perfectly serial schedules. That's crazy. Okay, but what we would like is actually what's called serializability. So a serial schedule, yeah, that's fine, it's great, but not realistic. The solution is to allow for serializable schedules. So these are schedules that are equivalent to some serial schedule, right? And this is where we can actually allow for some parallelization, right? So we can allow parallelization if we allow for this notion of serializability rather than strictly serial. Okay, so if any questions, just bring them up, and I can repeat stuff if it gets. I mean, this stuff actually can get a little bit tricky, but hopefully you guys are following along pretty well so far. All right, so we have two notions of serializability. We have actually what is like essentially the truth of serializable, and then later on we'll see that we have to kind of back off from that because of its properties and go to something that's a little bit more restrictive, but is still serializable. But it doesn't capture all potential cases. So what we're gonna look at first here though is this kind of semantic or kind of meaningful notion of what serializability means. All right. So this is kind of the correct notion of what serializability is. This is a sound and complete characterization of serializability. All right. Conflict serializable is what we're going to get to because we're actually going to have algorithms to enforce that. All right, so here are the three conditions surrounding view equivalence. Okay, so the notion here of equivalence has to do with our two schedules equivalent. All right, and that is what we call view equivalent. So this because we're defining view serializability here. All right, so if we have a set of transactions, and then let's let S be the schedule for them. We say that transaction I, in this case, could be transaction 1 through M, whatever it might be, reads X from transaction J. If the write action is happening in J before the read action in I, and there's no other intervening transaction who's doing a write. Okay, so it's like this, like if we imagine we have 3 transactions going, and the first thing, let's just imagine we have 3 transactions going, and we just have one data object called X, okay? And then what happens is the first thing that happens is transaction 1, let's call it, let's say that's John. We have John, Susan, and Laura, okay? And the first thing that happens is John takes X, and he writes a value into X. The next step is that Susan reads X. She is reading X from John. So Susan reads X from John, all right? And then let's say she writes X, and then Laura reads X, then Laura is reading X from Susan, okay? So that's basically saying, who are you reading a write from, right? And then of course, sometimes you're doing the first read, so you're doing the initial read. So that is, initial read is basically a read where in the schedule, no one has done a write of that object beforehand, right? So you're doing the initial read. And then we also have the notion of a final write, okay? So that is that I'm doing a write and there is no other transaction who will do in the schedule who does a write after me, all right? So that's basically the reading from, who reads what from whom, and what are the initial reads and what are the final writes, okay? So as long as these stay the same, then the two schedules are view equivalent. All right, so that's the key thing here. So if we look right here, we look at this schedule here, we see that in transaction 2, so right here, transaction 2 is reading this from the write of transaction 3, right? So it's pretty easy. So all right, so is that what's you might say where's the final write of Y? All right, the final write of Y is right here, right? And it's 2 that's doing it because there's no write after that of Y. Where's the final write of X? Oh, it's right here. That's the final write. Where's the initial read of Y? Well, the initial read of, right here, that's the initial read of Y, all right? That's an initial read of Y. Initial reads can be a little bit tricky though, because you can say that if let's see if we can say we read of Z. If this right here was right here, we also had a read of Y right here, and because since no one has written Y, then then 3 would also be doing an initial read of Y. Okay, so these are just kind of definitional, but hopefully, I mean, it should be pretty clear if I just set up one of these schedules and I ask you, okay, what's the where's the initial read of some object? You should be able to figure it out. It's not that hard if you think about it. All right. So the key thing here, though, is that these have to, for us to keep view equivalents, we have to keep these the same. So let's look at right here. So view equivalent. So this is the idea that when two schedules are view equivalent, if every read action in each schedule is either an initial read or else reads from the same write action. So it's doing all of its initial reads are the same, and all of its reading from writes is the same. Okay, so there's no change. And also the two schedules have the same final write steps. So they all do the same final writes. Then if two schedules have that, then they're called view equivalent. Now view serializable basically says that S is said to be view serializable if there is a serial schedule S prime such that it's equivalent to the actual schedule. All right, so let's look at this. This is kind of a realistic schedule. If we look at this schedule here, we have the, transaction 1 is reading X, reading Y. Then transaction 3 reads Z, writes Z. We have all this. Now, if we look at this right here, and then you ask yourself, all right, so what's the initial, we just say something like this. We say, all right, given that right there, what's the initial read of Z? All right, well, there is no initial, well, there's the initial read of Z. Initial read of Z is right there. Okay, that's initial read of Z. All right, in this case here, transaction 2 is reading Z from who? From transaction 3. Okay, now, if I do the following, that is, I basically take this right here, this does not pertain to Z, this does not pertain to Z. So if I move this right here to here, and that gives us this schedule here, right? That will give us this schedule here. Actually, this writing of Z is also being moved. So the write of Z, since these are not, so the read of Z and write of Z, these are both going to be moved over to here, all right? But when it does that, it doesn't change anything about what are the initial reads. All the initial reads are still the same. All the reading from a write are all the same, and all the final writes are the same. Okay, so that basically these are view equivalent. All right, so basically I've moved this over to here, and then now if we look right here, we say read X and read Y. X and Y aren't even in here, right? So the initial reads and all that are final writes. It won't make any difference at all. So I'll take these and I'll just move them to here, right? And now that I've done that, now that I've actually done that, then, and this read of Z looks like it moved over as well. You can see that these are also, these two are view equivalent. But the key thing is that this initial schedule here is view equivalent to this, since it's transitive, it's view equivalent to the serial schedule. Therefore, this schedule here, this initial schedule we had here is, maybe I made a little typo there, but I'll fix these in the slides later. Oh no, this is right. Yeah, so this initial schedule here, this initial schedule here is view serializable, okay? Because it is view equivalent to a serial schedule. Is that clear? Does it make sense to people? Okay, so we're still kind of at the theoretical, a little more theoretical stage here, but hopefully that makes sense. Now, this one right here, though, this schedule here, no matter how you try to permute it, how you try to shift things around, you can try for a long time, and in fact, you'll be forced to try for a long time, because this is the whole process is intractable from an algorithmic point of view. There's no way you can reach a serial schedule. Therefore, this schedule here is not view serializable. All right. Now, if we go back to this one right here, if we look at this schedule here, first of all, is this view serializable? Anybody want to answer in the? Yes, that's right. The ordering of the transaction is chosen arbitrarily. Any serial ordering is legitimate. Just like I was saying in the whole compounding and withdrawal example before, putting T1 first or T2 first, they both make sense. You can't argue with either one. They both make logical sense. Just kind of arbitrarily, you pick one. So the same is true with serial schedules. So yeah, so basically, if you have 10 transactions, you're going to have 10 factorial number of possible serial schedules, all right, that they're going to execute. So this schedule here, is this view serializable? Well, maybe the first question would be, is it serial? And the answer, this is a serial schedule. Because this schedule here, the one I'm showing in front of you guys, shows 1 going and then 2 going. I just got did you guys see that error message I got saying my internet connection is unstable? I hope that doesn't mean that we're going to go into trouble. How many guys are here? Oh, good. Well, everybody's still around, I guess. But that's a little bit scary. Good. Yes, you guys saw that gray box. Yeah, the gray box said on it that that the internet is unstable. Let's see. So, yeah, hope to stay with you guys. Here, let's see here. What are we doing for time here? Ooh. Right. Okay. All right. So this however, we go to this. We go to this schedule. However, okay. All right. So basically, transaction 1 reads X, transaction 2 reads X, transaction 1 writes X, and transaction 2 writes X. All right. So now we got a little bit of a problem here. So our problem is that for us to get a serial schedule, first of all, this final write can't change. So we're basically stuck with the writing of 2 in the final position. We can't move that. So that's given. Okay, this one here. So if I say that I want to basically move, I want to change this with that place. I want to change this step here with that step there. Then it would make it a serial schedule. But the problem with that is that if I did that, then transaction 2 will actually be doing its read from the write of transaction 1. And that's not what's happening in this schedule here. So this schedule and the one where I take this and change with that are not view equivalent. All right. And so no matter how I try, I cannot get a serial schedule out of this. All right. So theory says that this is not going to be view serializable. I cannot make this serializable. So it's kind of problematic. All right. Yeah. So I'm just going to skip over this. I'm going to you can read it later, but just take it on faith that both those conditions are necessary. All right, now there's another way of writing all this, and that's this thing called the direct serialization graph. Okay, so direct serialization graph is just kind of a more convenient way of writing these initial reads and then final writes and reading from a write. So what it basically does is you build up a graph. You're going to build up a graph of all the transactions. Okay, so each transaction is going to wind up getting a vertex in the graph. Okay, and then what you're going to have is basically, if I'm reading something and then these ones make sense. There's a write
conflict, and there's a write-read conflict, and there's a read-write conflict. So basically what it says is if I just read something and then you were the first other transaction to write it, then there's going to be a read-write conflict between us over the object X. All right. If I just wrote something and then you're the next one who writes something, then there's going to be a direct write-write conflict on that. And what these conditions here, where it says the implication of I, that basically it's saying there's no other transaction intervening between the two. And then a write-read is basically I write something and then you do a direct read of it. Okay, then there's going to be a write-read there's going to be a write-read conflict between us in this graph. All right, and then so this is essentially a way to encode the same kind of information that this view serializable definition is encoding, but this has a little bit more to it because it's doing write-write conflicts, and also it's better because it's, as we see, we actually use this thing in algorithms. Okay, so let's look at a direct serialization graph for a schedule. So for all these three schedules, it's the same. So if they're if two schedules are view equivalent, they're going to generate the same direct serialization graph. Okay, so what we see here then is we see that, okay, T1, write Y, so to 2. So T1, transaction 1, does a write of Y here, right? And then the next transaction, so 1 does that, the next transaction that does a write is 2. And that's why we have the write conflict there, okay? Over, I'm sorry, it's doing it right here. So it does a write of Y, and then 1 does a write of Y, and then 2 does a write of Y. And that's why we have this write conflict on Y that shows up here. All right. Likewise, we have a write read on X. And why does that happen? Well, because we have a write of X for transaction 1. There it is. And then we have an immediate read of X in transaction 3. It looks like the next read of X happens in transaction 3. And so that's why this gets drawn. We have a write on X as well, and then we have a write read. So what we're going to see here then is what we're going to see with this direct serialization graph is that as we're building it, so this is actually going to now give us an algorithm, right? As we're building the thing, the moment we see a cycle develop, then we have a conflict. Then the schedule that's going through is not serializable, all right? So once we see this conflict happening, then we know that this makes no sense, that we're not going to get a serial schedule. And therefore, one of the transactions must die, must be aborted from above by the transaction manager. It needs to say out to have it so that there's no cycles in the DSG. Okay, so that's why this becomes practical as an implementation. And we'll see a little more of that later. All right, so this is this notion of finding cycles, though it's a little bit more restrictive, so it happens more often. So sometimes there can actually be a cycle. And actually, so what I said was actually wrong. You can actually have a cycle. You can have a cycle, and just because of some peculiarities, it still actually is a serializable schedule. All right. So this is not a perfect measure, but the notion of conflict serializable says that once you have a cycle, then you consider them to be non-serializable. That's not always true, but the benefit of that is that to search for these is it's a very simple algorithm, whereas to search for view equivalence and all that, that's basically an NP complete algorithm. So it's an intractable algorithm. Okay. So conflict serializability basically says that so if two schedules are conflict equivalent if they have the same DSG, and they are conflict serializable if there's a serial schedule for and the theorem, of course, is that if a schedule for S is conflict serializable if and only if the associated a DSG is acyclic. So if it's acyclic, then we know that it's conflict serializable. All right, so we're guaranteed that. And then every conflict serialized, well, not only that, it's sound complete. So if it's it kind of rests on the definition of conflict serializability. But if it's conflict serializable, then it's also view serializable. All right, but not the inverse. So we're missing a little bit here, but it's not, as a practical matter, it doesn't matter that much. Okay, so the advantage of conflict serializability over view serializability is that it is simple and highly tractable algorithms to construct the DSG and testing for cycles in it. Okay, so what we've shown here then so far is really more theory. Okay, it's the theory of transactions, and it's a little bit dry, of course. But what we want to look now at is we want to look at how we're going to realize these things. So it's not, I mean, it's pretty clear that we don't want to have a situation where what we're doing is we're looking at, we look after the fact at a bunch of transactions that went after data, made changes and did their reads and their writes and all that. And then later on, post facto, we're going to declare whether or not it was a serializable schedule. that doesn't make any sense because we've already let people do the work, and now we're violating durability because they thought that the work is done now, but we've noticed, oh, actually that wasn't good. That's not a serializable schedule, so we have to back away from it. No. What we want is we want to have something where we actually can control this as it's unfolding in real time, so that we guarantee we have a mechanism so that we guarantee that we only allow for serializable schedules to come through. All right. So there are several ways to do that, and the primary one we're going to look at, this is for historic reasons, today is going to be locking. We're going to look at the way that you can enforce this with locks. Then there's the way it's really done now in terms of databases. Pretty much all databases except for DB2, I believe, is via multi-versioning. Okay, and I think SQLite does a locking as well. I don't think they're using multi-versioning, but I can check on that. We'll be looking at locking as a mechanism to enforce concurrency control or transactions. Okay, so let's take our break now, I think, and let's get back at 10 after. Yeah, let's get back at 11:10, and then we'll resume at that point. Okay. Okay, everyone. I think we can start again. I'll just give it, right, I'll wait for it to officially start here. It's still 11:09. If there's any questions, put them in the chat. La-da-da. Everybody's back yet? Okay, now I'll start. Okay, so the way we're going to enforce the conflict serializable schedules is through locking. All right, so we have the notion of a write lock and a read lock. All right, so now we're going to have writes and read locks. So a write lock has to be exclusive. So you can only one transaction can hold a write lock at any time. And when you hold a write lock, you also implicitly hold a read lock. Read locks, however, can be, as long as no one else has a write lock, you can, as many transactions as they want can have a read lock on something, right? And then to obtain a write lock, if a whole bunch of transactions have a read lock on something, then you have to wait for them to release it, okay? So locks are, what we do is basically we talk about lock requests and unlocking actions. So that the actual steps of the transaction now are enriched with these requests for locks and releases of locks, right? So a transaction with locks is simply just an enriched transaction set of steps where we have the reading and writing, read and write lock requests, and then the lock releases as well. And of course, there's some rules here, and this is kind of obvious. That is that you can't basically start writing X without having a write lock on it. And likewise, you can't read X unless you have a read lock on it. Okay, so these locks actually matter, right? Okay, so here's some examples of the transactions with locks. So if we look at this transaction 1 here, where you're going to read X, you're going to read Y, you're going to write Y, you're going to write Z, then these are all schedules with locks for T1. So basically what we see here is we say that we're going to get a write lock on X, a write lock on Y, and a write lock on Z. So that gives us the read and write locks on all those items, and then we do the operations, and then we unlock these items as well. So you have to, at the end of the transaction, or somewhere in the transaction, you have to unlock the locks that you're not going to be using anymore, right? So you can't hold a lock and then never give it back. I mean, that's not fair, or that's not, the lock manager will not let that happen. So if you commit, you release your locks. All right, so a schedule with locks it's kind of obvious. It's just now we have these lock requests and these lock release actions as well. All right, so so here's a non-serializable. Okay, so this was the non-serializable schedule we considered earlier, and this is a possible way in which we could get the locks for. So you can study that later. So let's just talk about kind of generally how this gets implemented. So there's something called two-phase locking protocol. So in two-phase locking protocol, what we do is we impose the following conditions over locks inside of transactions. And that is that you have to gain your locks in a growing phase. So you're going to make all your lock requests, and then you're going to release your locks in a shrinking phase. So for something to be two-phase locking compliant, you can't request a bunch of locks. I say I want a read lock on X, a write lock on Y, and a read lock on Z. Now I'm going to release the read lock on Z, and I'm going to grab a write lock on W. No, that's not 2PL anymore. Because what I've done is I grab my locks, then I start releasing one, and then I grab another one. So no, that's not that doesn't conform to 2PL. So if you go to 2PL, so if you actually if you conform to 2PL, so the schedule is in two-phase locking, then basically you guarantee that you're going to be conflict serializable. So what's nice about this is that actually two-phase locking, if you make sure that all the transactions respect two-phase locking, you're going to get as an outcome a conflict serializable and thus a view serializable schedule, right? So that's all it comes down to. That was it. That's how locking actually helps us. There's a theorem you can go through, you can push through the proof that this is actually going to give you a serializable schedule. So that's all very good. It's very good, a very good result. All right. So so again, remember, all you're asking, that basically all you're doing, only condition you're putting on it then on transactions is that they acquire their locks, they do their work, or they acquire locks, they do some work, and then acquire more locks, whatever. But once they start giving up locks, they don't grab new locks. That's the key thing, right? That's all 2PL is. So if we look at it though in, so to what extent is it useful in real systems? Okay, so there are a couple of issues though that we need to kind of add on to two-phase locking to make it practical. So the most important one is this notion of what's called recoverability. All right. So this right here, as we'll see, is something that's quite critical to maintain durable transactions. This idea of recoverability. So basically, what it says is that if a transaction does not finish normally, that is, if it aborts, it must be handled in a way to preserve the integrity of the remaining transactions. And then we also have an issue of management of deadlocks. Okay. So these are kind of two issues that kind of come in. So let's look at the issue of the recoverability of transactions. So transactions. So here's the crux of the problem. What if a transaction aborts after executing at least one write operation? So I'm a transaction, and I read X, I write X. I get a lock on X to do writes. I read X, because I can do that now. I write X, fine. And then I write X, and then I even release the lock on X, okay? So now somebody else can get a read on X. I'm still going though, right? I'm still going. But another transaction now can read X, right? And then they can go and do a whole bunch of stuff with it, and they can even maybe commit and do something, they can do whatever they want. But meanwhile, I'm going along now, and oops, I divide by 0, or I run into some kind of intractable state here, and I have to abort. All right, so I abort. The problem is that I had written out X, and I had released the lock on X, and somebody else got that lock, and they read X. And God only knows what they did based on what I wrote to X, right? So what I've done is I've done what's called a dirty write. I've done a dirty write. So I've let loose dirty stuff in the world, because it's not valid what that write was, because I'm aborting now. So whatever I did before, I'd like just to roll it back and say, I don't want to, I didn't mean to do that, sorry. But now it was a dirty write. So somebody read that dirtiness out there. So now it's gonna influence stuff, and everything's kind of out of control. So whoever read that dirtiness has to be chased down and aborted as well. But they may have already committed. So their user might think, wow, that's fine, I'm done now. So that would then go against durability. So that's bad. That's really bad. So we cannot have that. So it could potentially lead to what's called cascading aborts of transactions that have already committed. All right. So if you look at some really kind of a detailed example here, well, this is the example I was talking about before. I read X, I write X, and then I unlock, I release the locks on X, and then transaction 2 reads X and write X, and then transaction 2 commits. But then I go on and I read Y and I write Y, but then I abort. So transaction 2 is it read dirtiness. All right, so it was a dirty write, or a dirty read. So the transaction, I did a dirty write and transaction did a dirty read, but either way it's dirty. Okay, so that's bad, and it can cascade arbitrarily, as this example shows here. So we've got to prevent that. All right, so what we need to do is we need to make sure that all of our schedules are what's called recoverable. All right, so a recoverable schedule technically means that that RJ reads from, if transaction J reads from transaction I, it implies that transaction I commits before transaction J. Okay, so that's kind of what it means. But as we'll see, there's a real practical way of doing this in 2PL. So in 2PL, the key issue is just not to release the locks. So if you do what's called rigorous 2PL, you can avoid this non-recoverability problem. All right, so all we have to do to fix this is very simple. All we have to do to fix this is we basically say that, sure, you can go through your growing phase of acquiring your locks as a transaction, but then you've got to hold them all the way to the end until when you commit, and then after you commit, and only after you commit, are those locks released. Okay, so the committing is also basically tied up with releasing of all the locks. All right, because what that does then is it makes sure that I'm committed before anybody can read from any of my writes. All right, so therefore, if I'm committing, then presumably all of I don't have any dirty writes, and then they're not doing any dirty reads. Okay, so that's the notion of rigorous two-phase locking. All right, so it's fairly easy to implement. In fact, all you do is you basically just say you've got to hold all your write locks until the very end. Okay, there's a question about whether or not you need to hold all your read locks as well. Technically, no, if you want to think about that, but we'll just say all locks. You have to hold all your locks until the very end. Okay, now, so now we got a problem with the growing phase. So in the growing phase, well, we can arrive in deadlock positions, the deadlock situations. So we have a situation where we have this. We have two transactions. All right, so suppose we have a schedule where we get a write lock. They both want to, transaction 1 wants to write X, and transaction 2 wants to write Y, but transaction 1 is going to get a read lock on Y, and the transaction 2 is going to get a read lock on X. So basically, what would happen if these have their read locks? Then if transaction 1 comes up to the point where it's grabbed a read lock on Y, and transaction 2 has grabbed a read lock on X, but then they want to grab the write lock on X or the write lock on Y, but vice versa, then we've reached a deadlock position. All right. So basically, neither can progress. All right. So that's a deadlock. So the way you can detect the deadlocks is you can simply have this kind of wait fors graph. So where you basically say who's waiting for what lock. Okay. So in this wait fors graph, we would have something like this. Basically, we have okay. The lock sets. So basically, what we say is the wait for graph is going to be this. It's going to be that T1 is waiting on X from T2, and T2 is waiting on a release of Y from T1. All right. So once you have a cycle in this waits for graph, who's waiting for what, then you have a deadlock situation. All right. So the way you resolve deadlock is you need to basically what you need to do is you need to abort one of the transactions so that you force it to release its locks. One sec. Jag håller på föreläsning nu. Ja, hej. Okay. So there are two ways to deal with it. There's one way. There's only really one way here that actually gets implemented. Pessimistic is you don't allow a transaction to acquire. A transaction needs to at the very beginning declare all the locks it needs. Okay, that's pretty hard to in many real world cases you can't do that. because you don't know, as the transaction unfolds, you don't know what the customer is going to do. They start the transaction and they're going to start reading, and then maybe they want to, then finally, after they made a decision, they want to get a write lock on a particular tuple that represents a plain seed or something. So it's very, very difficult it's in many cases, it's impossible to anticipate, unless you're going to lock the whole database, which you don't want to do. It's very hard for you to anticipate what the locks are beforehand, what's going to be required in a transaction. So what actually gets implemented most of the time is optimistic, which is that you do have this kind of wait for it graph, and then you know, a lot of times you have to based on what transactions are doing, sometimes the transaction needs to get aborted. So I'm sure that many of you have had that experience where you're trying to book a flight, and you get something, you know, up on the screen, this flashes this thing where you can select a seat, and then you select the seat, and then something weird happens in the interface, but then it comes back, and then you have to select the seat again, but the seat that you wanted to select isn't available anymore. Right? And the same thing can happen with like trying to select a flight as well. And that's an example where there's somebody else where isolation was broken a little bit, because somebody got in there and got it before you, and therefore, and your lock that you had on that, well, there was a little bit of a deadlock situation, and you know, there was a contention over that resource. They got to it first, and therefore you got aborted, okay, or you got partially aborted. So it happens all the time, and it's not that big of a deal, really. It's just, you know, they're not going to tell you that, of course. They're going to just let it happen and kind of make you think, well, it's just a little bit flakiness in the world. But most of the time, it's another transaction that got snuck in and got the resource first. All right, pessimistic resolution of deadlock is not realistic, so we're not going to talk about that. Optimistic, okay. So now, when you do the optimistic, so if you're going to do a lot of restarts of transactions, so in other words, they're getting aborted. What you want to do is you want to restart them with their old timestamp, and then always prefer, when there's a tie, always kill the younger one. Okay, so if one was younger at one point and got killed, then when it gets restarted with its earlier timestamp, so it will be older, and this will basically guard against this live lock problem where you're always being excluded and you're never being able to complete. So that's just a simple way to prevent this live lock or starvation problem. All right, so now we're going to talk about about what is being locked, and you know, what is the unit of what is being locked? What's the granularity of what's being locked? All right, so so at first thought, when you think about like what are you going to lock, you might think, well, it's best to kind of have the finest granularity possible on the locks. So this has the advantage, of course, of allowing a lot of parallelism, because if I'm able to lock, so the question is like, well, how fine grain can locking get? Is it going to be on it could be on a per database level. That's pretty coarse. It could be on a per table level. That's pretty coarse. It could be on a set of tuples in a table. Okay, that's a range lock. It could be over a single tuple. It may even be over a single value. But as we'll see, that generally speaking, the locks usually go down to the granularity of a single tuple and not farther. Okay, so one thing would be like, well, let's just have a lock on every tuple, right? That's a lot of locks, though, right? So that can be, so you can really have an explosion in the number of locks that are going to be managed. And also, another thing to consider is that different transactions might have require different locking granularity. So we might have transaction A, which is going to process a whole relation. So it kind of works best with kind of a coarse grain lock. So like something where it's going to like read and do an average of all the salaries or something. It's going to want to like just basically lock the whole table on a read lock, all right? And then you might have at the same time, you might have a different transaction which just wants to lock a few tuples at a time. So something where we're going in and we're changing the salary of a particular employee, or we're adding an assignment or something. That would be a transaction where it would make sense to lock just a couple of tuples, right, or one tuple. So if you have a lot of concurrent transaction B processes, you can get a lot of parallelism potentially, because one transaction B type process might be locking one particular tuple, the other one another tuple. They're not touching, so they can go concurrently. So there's going to be no contention there. So basically, it's advantageous to somehow support both coarse and fine-grained locks under the same system. And what we can do is we can actually do that with what's called multi-granular locking. So let's just look at this right here. So let's say that what the object that can be locked can be either the full database, a relation, a range query, right, or a single tuple. Now, and these are some examples. So the employee table, all the tuples with a salary greater than 40,000. That's also, you could potentially have locks, spread over all of those. And then we also have this, like the locks at the level of the individual tuples. Okay, so here's how it works then. Is that okay? So this is the hierarchy. So when an object is read or write locked, then all the objects below it are also read or write locked implicitly. So if I'm like an OLAP type query who's going to lock the whole employee table, when I grab a read lock on the full employee table, then that basically is going to mean that it's going to grab a read lock on everything implicitly. My read lock on employee is also a read lock on everything under it, right? So now, if as I'm running, there's going to be another transaction that wants to do a write on David here, that transaction will not be able to obtain the write lock on David until I release the read lock on employee, right? Okay. However, what's nice about this, of course, is that it's that if things are going at the tuple level, you're getting read and write locks on these, then you get a lot of parallelism. So if I lock Bruce, it doesn't mean that somebody can't. If I do a lock on Bruce here, it means that somebody can potentially get a lock on this range here. All right, they can get I got a read lock on Bruce. They can get a write lock on this because Bruce is not being touched there, right? So it allows for multi-granular locking allows for one system to kind of have locks at many different levels. All right, so now, actually we're making really good time here, maybe a little bit too good a time. I could have maybe spent a little bit more time, but I'd like to actually get some questions going maybe if people have them. But let's talk a little bit about the SQL standard and these degrees of isolation. All right, so the first thing to say is that the way that the SQL defines isolation levels is it basically defines them in terms of anomalies that are allowed. Right? So there's different anomalies that are allowed under different isolation levels. Now, this is traditional, and then we're going to look later on. We're going to look and see how it actually gets implemented in modern systems. But let's just go with these isolation levels here for the time being. So these all are a natural outcome of two-phase locking. So two-phase locking will kind of, under various kind of restrictions, will block against certain anomalies. Okay. Now, when we go to like the two-phase locking that basically says you have to hold the locks all the way to the end, right? What that does, so that's called read committed. So if you say that I'm going to hold the locks all the way to the end, then that prevents the anomaly of a dirty read. All right. So no one can read dirtiness because I can't write out. I have to commit before my write lock or my locks get released. Right. The non-repeatable read. So the non-repeatable read is an issue of, well, when a transaction does a read where it's going to read, like, let's say it's going to get give me the employees, and then later on in the transaction it says, okay, give me the employees again, then the set changed. So it's not as isolated as it had been before, right? So it's not so isolated because another transaction went and added employees, and then when I read employees again, I see the new employees. Okay, so that's basically that is allowed under this read committed. Okay, now repeatable read, what that says is it doesn't want to have that happen. So once you get the read locks on something, nothing else can write those out. All right. Now, what essentially happens here though with the So in the case of read committed, you basically says, well, I can anytime I want to read it, I can read it, and if somebody else commits it in the meantime, then if I read it again, I'll see the new version. So if you say repeatable read, then that doesn't happen anymore. Okay, that doesn't happen anymore. So once you read something, then if you read it again, then the same thing, exact same thing again, you're not going to see any new changes to it. All right. Now, what repeatable read doesn't block again is something called phantoms. So phantoms are something where it's like you have, I've selected all the employees, and I've got the tuples for the employees back. So I put locks on all those employees, but then someone puts another employee in, and that employee then pops up. Right. So repeatable read has to do with things that I got tuples for. If I read the tuples again, then they haven't changed. And as we'll see, actually, the phantoms have to do with locking over ranges. That's where they're coming from. That's where phantoms are coming from. Finally, serializable just means that we don't have any of these anomalies. So none of these anomalies are present. So that's the definition under the SQL standard of what serializable means, is that you don't have phantoms, you don't have non-repeatable reads, and you don't have dirty reads. What we'll see later in the next lecture is that does not actually correspond to serializability or view serializable or conflict serializable. It doesn't have a correspondence to that. So we'll actually find out that this is actually, it's kind of an interesting story behind that in modern systems. But the SQL standard just kind of goes by this. It doesn't go into the deeper level. It just says about the non-presence of certain anomalies. Now, the one thing you'll notice here, there's one anomaly that we talked about earlier today that is not actually mentioned here. And that is the anomaly of the lost updates. So when one transaction clobbers the other. If you want to get that, then basically what you do is you don't even use transactions at all, right? Then you just, if you don't use transactions at all, so everybody's just doing reads and writes without saying begin or commit, then you'll actually be able to have that. You'll have much better performance speed-wise, but then you'll wind up having the possibility that logically one transaction's updates are clobbered by another. Okay, so we're gonna just kind of go through this again. So this, I just said, in verbally what I just said is kind of now captured here in these. So let's just go through so that we can kind of nail it down if we have the time here. Yeah, we have the time. So let's just kind of repeat, let's just kind of do this again here. Okay, so degree of isolation number 1, read uncommitted. So this means that under this isolation level, if another transaction writes something out, but they haven't committed yet, I can read it. And that's potentially a dirty read. Okay. So that was this example of having non-recoverable schedules. So read uncommitted. Are you ever going to have a situation where you want to run something under read uncommitted? Potentially, there might be. So a nice thing about something like this kind of very, very low level of isolation, this very, very weak isolation level, one of the advantages of those kind of things is that it allows you to get a better performance. So you can do throughput is much higher. Okay, so there might be cases in which this would be allowed. So for instance, I mean, I think things where you're not doing a lot of reading of other transactions, but or it's something that, let's say, we can think of some examples here where that might actually be useful. Under read committed, so if you run your transaction levels under read committed, then what that means, it means you're only going to be reading, when you don't do a read of something, you're going to be reading what's already been committed by another transaction. However, another transaction might also alter the data, so you might get non-repeatable reads. So the reads are like, in one case, you get the read of these are the values for the employee and the employees with their salaries and all that, and you do it again within the same transaction, and the read changed because somebody else committed underneath. All right, so here's an example of that. And then the repeatable read is this issue with this phantoms. Okay, that come in. Okay, so yeah, I think we're actually going to be able to end a little earlier because I don't want to go on to snapshot isolation today. the cover here just as simple is this, is that, yeah, so the serializable, so the SER mode of standard SQL is view serializable, no. So it's just getting defined in terms of the absence of these anomalies. So then, but surely the major database management companies implement the standard SQL serializable as like rigorous 2PL. All right, so when we're going to go out to multi-version concurrency control next time, this is actually how they implement things. And what they do is they use something different called snapshot isolation. And that's the strongest level of isolation that until recently they were maintaining. However, as it turns out, there were some anomalies that are not among these anomalies, not among SQL anomalies. There were some other anomalies that were discovered that actually were sneaking into snapshot isolation. And then it was interesting because it set off a fair bit of activity where they did a repair to the algorithms inside the databases, kind of as a bit of an emergency because there was a weakness that had been found in terms of these some anomalies that we'll cover these the next time. Some anomalies that were allowed to creep in, and then of course the thing about these anomalies is you have to always remember with anomalies and transaction processing, it's like you might say something like, oh, well, the chances of that anomaly actually happening are very, very rare. And that's true. But again, remember when money is at stake, that people are going to concoct cases which are going to go to that degenerate case to do exploits. So in fact, I think there was a Bitcoin exchange that was bankrupted because of some issue they had with they were running things under read committed, I believe, and a clever attacker was able to bankrupt them by setting things up just right. So again, when there's anomalies in transaction processing, they will be exploited. So that's not a good thing. So as it turns out, snapshot isolation had some weaknesses in it, but they've all been patched now. But we're going to go over that in the next lecture when we talk about the way transaction processing is really implemented in modern systems. So what we covered today was kind of more theoretical. I do apologize. I kind of went a little bit slow in the beginning and fast toward the end. So I think it probably requires a bit of study for you to kind of really absorb what was covered today. But if there's any questions right now, I can take them. Or if everybody wants me to do an example, let me know. But we'll clear all this up through recitations, and it's coherent. I mean, there's makes sense. So are there any questions now at this point? Yes, this video will be posted on Cambro. Yeah, they're all there. By the way, if you go to the overview on Cambro, there's on lectures. If you click on lectures, it'll take you to these unlisted YouTube videos. So
I think you will find them in files and then resources, something like that. You will see them in the HTML. This is where I found them.
Yeah, that's right. They're there, but I also updated it so that you can just click from the overview page now. Because I think somebody said that they thought I should make it so you just click, and then when you click it, it'll just take you to an HTML thing where it says lecture 1, lecture 2, lecture 3, lecture 4, and now lecture 5. I mean, I'll post this lecture up there later today.
They are on content. If you click at all site files, you will find them on lectures HTML. It's there.
Yeah.
Yeah.
Great.
Thank you.
Yeah, thank you. So are there any more questions at this point? Again, I'm sorry I kind of rushed things there. It's a little bit, don't feel bad if you don't get this. I mean, this takes a bit of study to see all the ins and outs of transaction theory. So, but we'll have a recitation where we're going to go through this in detail. I'm not sure about task scheduling in Windows and how that relates to transactions. But a lot of this stuff does seep in. A lot of these I mean, it's not just databases that took advantage of this kind of transaction processing kind of findings, but of course we've presented mostly under database guys here. But I think what's unique about databases when it comes to transaction is that it really explores kind of the structure and kind of the granularity of the data. So what's going on? I mean, you'd say something like, well, I mean, Unix has some kind of naive way it does transactions, and the way it does locking, but it's much more sophisticated in a database. I'm not really sure about Windows. But okay, so if there's any other questions, let me see them now. But otherwise, I think I can end this. Okay, great. All right. So yeah, so keep me posted on what's going on with your project. So if you haven't had your project, here, let me just stop the lecture here, or the recording.